Hi, this is Al, your probability and statistics instructor. Okay, time to start talking about probability theory. Today's topic will be that, the concept of a Borel field. Well, before we get to talk about Borel fields, we will need to introduce a couple of things. Okay, we will need to discuss a couple of concepts. Infinite sets. We will have to talk about infinite sets first. Another thing that we will have to talk about is De Morgan's laws. Well, let's begin with infinite sets. What I want you to bear in mind is that not all infinite sets are equal. Not all of them are the same. It turns out that infinite sets come in two different flavors. One of them a countable set, the other one a non-countable set. Let me give you the definition of a countable set. An infinite set is called countable if all of its elements can be arranged in a 1-to-1 correspondence between them and all positive integers. Let me give you one example. Of course, the set of all possible integers itself. Clearly, we can establish a 1-to-1 correspondence between them and the positive integers. And the formula, if you will, that relates them would look something like this. If C belongs to the set of positive integers, then the formula, the function that establishes the relationship between the set of positive integers and this set here, 1, 2, 3, 4, so on, would be this, the identity. Make sense? If you have a 1, then you assign it to 1. If you have a 2, you assign it to 2, and so on. So there's a 1-to-1 correspondence between those two sets. Another example. How about just pay attention to odd numbers. Is that an infinite set? It is. Is it a countable infinite set? It is. And we could convince ourselves that that's the case if we have this formula here. Let me be lazy and copy this. So one way of showing that there's a one-to-one correspondence between these two sets, the set of positive integers and these guys, is giving a rule, a function to assign them and show that that relationship, that function is one-to-one. Okay, so for instance, if we have a 1 here, then 2 times 1 minus 1 gives you 1. So it corresponds to this guy. If it's a 2, 2 times 2, 4 minus 1, that's 3. 3. 2 times 3 minus 1, 5, and so on. So there's a one-to-one correspondence between the set of positive integers and the odd numbers. Okay, so that's one flavor. These are examples of countable infinite sets. How about uncountable sets? First, let me tell you how we are going to be defining these guys. If non-countable set is one where the above mentioned one-to-one correspondence cannot be established. And I'm not going to show you this, but I'll give you an example of a non-countable set. So an example of a non-countable set would be this set that I'm calling C, formed by all numbers x such that x is greater or equal to 0. So basically what we have here is the set consisting of all non-negative real numbers. So one can show that the set of all non-negative real numbers is, well, has more elements than positive integers. Therefore, is a non-countable set. Okay? Okay. So now that we have established what countable and non-countable infinite sets are, let me move on and talk about the other concept that we're going to need, the Morgan's laws. So, by the way, I'm going to ask you to do an exercise related to these laws. But before I tell you what that homework problem is going to be, let me state these laws. First, of the Morgan's laws. It has one part. First part is this: the intersection between sets or events A and B is the same as the union of the complements. So A intersection B complement is the same as A complement union B complement. Okay. That's the first one. Second one. The second one has to do with a very similar expression, but instead of an intersection here on the left hand side, we're going to have a union. A union B complement. If you had to guess, what do you think we're going to have on the right hand side of this expression? Well, I'm sure that you guessed it right. I'm sure that what you said was A complement intersection B complement. Those are the Morgan's laws, and something that I'm going to ask you to do is kind of a homework problem. I will ask you to do exercise 2.3. In that exercise, what I'm asking you to do is to verify the Morgan's laws using Venn diagrams. Now, we know that Venn diagrams are not the formal way of showing this. Okay, but I just want you to keep it in mind, give you some intuition, and then if you want, we could maybe during office hours, maybe we could discuss how you could show that formally, or remind you how you would do that formally, because I'm sure that you have seen that sort of proofs before, like in Math 102. Okay, so we are done with the second concept that we said we needed to discuss our main topic of this video, Borel fields. So let me define what a Borel field is. So given a sample space S, a Borel field is class of subsets, okay, that has three important and very particular properties. I'm going to list those properties in just a minute. So given a space S, you know that we're going to be using that capital letter S to denote the sample space. A Borel field, some people refer to them as sigma fields also. Also known as sigma field. So a Borel field of subsets of S is, as I said, a class of subsets. Let me use A for the events, the subsets of interest. J for the subscript of or subindex, and J will go from 1, 2, 3, so on. And these guys have, well, these guys, Borel fields, have the following properties. Number 1, S, the whole sample space, belongs to the Borel field, okay? And I'm going to be using the letter beta to denote the a Borel field. Yeah, beta. So S belongs to beta. The Borel field. The other property, the second property, is that if a subset, if an event AJ belongs to beta, the Borel field, then its complement, AJ complement, will be M beta, the Borel field. Okay, so if AJ is in beta, then its complement will also be in beta, the Borel field. And the third one is a very important one. It turns out that if we are dealing with a Borel field and we have a sequence of events A1, A2, A3 up to, right, an infinite countable infinite number of events, then the union of that countable number of subsets Aj will also belong to beta, the Borel field. Let me write it down like this. If Aj belongs to beta, our Borel field, and it turns out that we have an infinite number of them, right? We have 1, 2, 3, ... Then the union, the infinite union of these guys so let me write it down like this. A one union A 2 union A 3 union ... will also belong to beta. Okay. A fancy way of expressing something like this would be having this, our our funny looking U that denotes union, but then using our subscript J and then let me see, yeah, we have it here, and use that infinity symbol. Make sense? It's the same thing. It's just we like our fancy notation in math and probability. Make sense? Just notation. Okay. So, bottom line, what I want you to remember is that Borel fields are a special class of subsets, right? With these three properties: that you have the sample space being part of that class of subsets, right? If you have events, if an event belongs to your Borel field, your sigma field, then the complement also lives there, it belongs to beta. And then if you have infinitely many of those subsets, then the infinite union of those subsets also belongs to beta, the Borel field. Make sense? Okay. So let me, now that we have our definition of Borel field, let me talk about some important properties. So two important properties that we have as a consequence of these three characteristics that define a Borel field, right? We have two important properties as a result. So one of them is this. Note that we said if, well, by property number one, the sample space belongs to beta, right? Okay. So if that's the case, by property, let's do that. Property number one. So S belongs to beta, to our Borel field, right? That's just by one. By property one. Maybe we should call these additional properties. Okay. Now, by property 1, we know that the sample space belongs to beta. But it turns out that the complement must be in beta by property 2, right? Okay. This is just by the second property. And then, what's the complement of the entire sample space? The empty set. So therefore, as a consequence, we have that the empty set lives in beta, our Borel field as well. Make sense? Okay. So that's our first additional property. Let me call it I. Second additional property. Let me write it down like this. Say that we have again an infinite sequence of events. A1, A2, A3, dot, dot, dot. And those guys are in beta, belong to the Borel field beta. Then what we're going to have is that their complements also live in beta. That's right. And that would be by property number 2 of a Borel field. Make sense? Okay. So let's say that their complements will be there, part of beta, just by the second property. Okay. Property by property, let's say that. By property 2. But by property 3, the union of those guys belongs to beta as well. You guys agree? Okay, so let me write it down using our fancy notation here. So the union, the infinite union, but now we have complements, right? These guys live in beta, then the union, the infinite union of these guys must also live in beta. Oh. There we are. Nice. And that would be just by the third property. By property 3. Finally, remember that we discussed the Morgan's laws, right? So, it turns out that the union of complements is the same as the intersection of those subsets, the whole thing complement. Make sense? Okay, so let's do that. Let's write that down. So instead of having this, the union of complements, we're going to have the intersection of the sets, the whole thing complement. So this guy here, instead of that U that denotes the union, we're going to have intersections. Instead of having complements, we're just going to have the sets, and here what we're going to have is the whole thing complement. Make sense? That's by one of those De Morgan's laws that we talked about. By De Morgan's laws. Now, if this guy, let me call it C, right? Let me call this the intersection of all these events, the event C. If C complement is here, then C I mean the complement of that guy, which would be just C, must be there, right? So we're done. So basically what I want you to remember is that these three properties, the original ones, the ones that define a Borel field, that the sample space belongs to the Borel field, that if an event belongs to the Borel field, its complement belongs also to the Borel field, and also that infinite unions are part, belong to the Borel field. With this 3, you get these two additional properties for free. That the empty set is in the Borel field, and that infinite intersections are also there. Okay? Now, why is this going to be important? Because in another video we said that more often than not, we're not just going to be interested in simple outcomes of a random experiment. We're going to be interested in combinations of events, right? And by combinations of events, what we mean is maybe unions, maybe intersections, complements, you know. So this concept of a Borel field will come very handy in the construction of something that we are going to call a probability space. Okay, so let's move on. I know that this part was kind of abstract, so let's try and talk about an example that is more concrete. Let's define a sample space S like this. It will be a set formed by 3 elements, or sample points we also call them. What I want you to see is that Borel fields are not that scary. They will be very useful, but they are not that scary, right? So hopefully with this example I'll show you what a Borel field looks like. Okay, so first thing, right? We have these properties we just showed. We know that if the sample space lives in beta, the Borel field, then its complement must live there as well, right? Okay, so let me create a set that contains as one of its elements the empty set. Then we also said that, well, in a Borel field, the sample space itself must live there. A, B, and C. Okay, that would be another element, well, another subset that would be part of our Borel field. Note that A, right, just A, that's a subset of the sample space. So that guy must live there as well. A. The same thing could be said about B and about C, right? That's a subset of the sample space, therefore it must live there in beta, the Borel field. Since A belongs to beta and B belongs to beta, then the union of these guys must live there as well. AB, AC, BC, and that's it. Right? So note that in this particular case, where the sample space is formed by A, B, and C, those are the outcomes. Well, this guy here represents beta, the Borel field. Okay? That guy satisfies those three properties that we talked about. The sample space is there. If a subset is there, its complement is going to be there. For instance, the complement of A will be B, C, right? And so on. And then the third one is you have a bunch of subsets of events. The infinite union, in this case, well, if you do an infinite union, well, you have only finitely many elements, so you can only do finite unions. But anyway, the union of these guys is going to be there, right? If you do the union of A and B, okay, it's here. If you do the union of A, B, and C, well, it's also here, A, B, C, and so on. And again, using the other property, you could find that the intersections also live there. Make sense? Okay. So, summary. What we talked about today are a few things. We talked about infinite sets. What we said about them is that not all of them are the same. We have different kinds of infinite sets, countable and non-countable. I wanted to mention the countable ones because we were going to be dealing with countable unions when we mentioned the properties of Borel fields. Okay? We also talked about De Morgan's laws. Why did we do that? Because De Morgan's laws basically establish a relationship between unions and intersections, right? And that helped us to establish additional properties for Borel fields, since the basic properties, the third basic property that defines a Borel field is stated in terms of unions. If we wanted to see how that implies that intersections are also part of the Borel field, we needed De Morgan's laws. And the other important, the main topic that we wanted to discuss here, that we wanted to introduce here, are Borel fields. And those guys are, as we said, class of subsets that satisfy three particular properties: that the sample space lives there, that if a subset lives in beta, the Borel field. Its complement also lives there in beta. And the third one, that infinite unions of subsets are part of our Borel field. Make sense? Well, that's it for now. See you next time. Take care and work hard. Bye.